Welcome, exam review of computer simulation and modeling. In this module, we have two lessons, uh, just an introduction to physics-based modeling and then the fundamentals of physics-based modeling. So in this introduction, we learned how to formulate a mathematical model, and then this mathematical model, if it has an analytical solution, we solve it analytically. If it does not have an analytical solution, we solve it numerically. Yeah. And we can always solve it numerically, yeah? Whether it has or does not have an analytical solution. We also looked at the fundamentals of the physical based model, like boundary condition, like finite difference method for numerical solutions, and inverse modeling or model calibration. Yeah, it's used for model calibration. The introduction to physics-based modeling. So we have dependent variable. That's whatever, like that's your hydraulic heads, that's the concentration of a contaminant, that is temperature, that is flow rate, whatever. Yeah, it's function of independent variable parameters and some forcing function. So in that case, for example, like my dependent variable was the velocity, my independent variable was like temperature, my parameters here was like the mass of the person, like in the parachutist, and some coefficient that's related to the parachutist, and then uh, the forcing function here was just acceleration due to gravity. We see we express this mathematical model as a form of a differential equation because we have like the dependent variable and its derivative. Both are expressed in the same equation. Initial condition at the before jumping, it was at rest. Like at time zero, the velocity was zero. We can solve for our mathematical model either analytical solution, numerically, like a numerical solution. So that's basically the basic concepts that you need to understand. So that's a mathematical model. We define it. Initial condition at v is equal, at time zero, the velocity was equal to zero. The analytical solution would look something like this. So if we use what we learned from calculus, integral calculus and differential equation, and how to do like integration by parts, then we get an equation that looks like this. But we can also get a numerical solution, and the numerical solution, by like, we can reformulate our mathematical model to solve it with arithmetic operations. Yeah. So basically, like the dv over dt, I can just express it by delta v for initial time step and like the next time step, and same with the time, initial time step and the next time step, and that would be uh, the velocity at the initial time step, and that's how I could calculate velocity at the next time step. And again, remember, like this dt and this dv, the smaller these things are, the more you'll be close to the analytical solution. Because remember, like the analytical solution is when the limit of dt approaches zero, basically. That's where you will get the exact like analytical solution. But you can get an approximate slope, and we learned how we can improve like our numerical solution. Like one way you use like a smaller time step, but another way uh, you use more Taylor series expansion. So instead of like just approximated like your first Taylor series expansion, you can go to the second, the third, and so on. Yeah, but like in that case, you would need more initial values. So like you wouldn't only need like some one initial value, you would need like two, and so on, if you are doing for second Taylor series expansion. But anyway, so you can formulate this, and then I would know like v at the next time, which would be like, that is what I already know, like my initial time step, which is, in that case, that would be the initial condition for the first time step, and like the delta t is like my time step. So I can formulate like new value is equal to the old value plus the slope times the time step. This is known as Euler method. Yeah. there are more advanced numerical method, but we didn't cover them in this course. Yeah, but you should be able, like the minimum that I expect from you, like you should leave this course by be able to do at least a numerical solution. They are tedious, I know, like that's why I didn't cover a lot of them. They are tedious, but at least you should be able to do. So in the exam, I will give you something that looks like this, and then I will tell you to calculate something, giving like different time steps, for example. So you see the time steps here is giving as 0 2 second, and compute the velocity at t is equal to 18 second. Yeah. So you can basically like formulate an equation like this and then calculate the velocity. You just like to, so this is the analytical solution. If I just like use the equations that look something like this, but this is a numerical solution if I use an equations that look something like this. So, okay. And remember, like that's like the old value plus the slope times the time step. So here, this is the slope. So here, this is the slope, and this is the time step. So the old value, would be here plus the slope, like, so I evaluate, like, so if I, how to get this value, like how to get this guy, for example. So that would be the old value, like 0, plus the slope, I calculate this one, times the time step, in that case is 2, then I get this value. Then how to get this value? So that would be like this value here, that's the old value, plus the slope, so I calculate like the slope from here, I multiply it by 2, then I got this value, and so on and so forth. Okay, we have seen like this is the exact analytical solution. This is the approximate numerical solution. And how can we improve this? So one way to improve this, for example, is like you take a shorter time step. And I showed you here because, like, see, the smaller it is, see, like now here, this is the exact analytical solution. See, this is the slope is not exact as, like, this is a true slope, this is the approximate slope. But if I take smaller DTC, like the true slope is very close to the uh, approximate slope, and then I get like a better solution. So here, for example, I took a very small like step size. So instead of going 2 second, I go 0.2 second. And then, like, you see, the approximate numerical solution is equal to the exact solution because I take a smaller time step. Yeah. So like numerical solution for identity, like one way you can do, like you can reduce the step size. Yeah. And here, like the root mean square error, like I can calculate the error between these two, that would be like very small. So at step size iterations, the root mean square error was like 3.12 meter per second. Like the difference between like this guy here, like at these points, and like the true solution was this one versus this one's very small error. We also learned about boundaries. So like, so in the exam you should be able to know this, like what's an analytical solution, what's the numerical solution, how to improve a numerical solution, and so on. Like, so you improve numerical solution by taking higher order Taylor series. I mean, I didn't show you this, but I mean, this is one way of doing it, because I didn't like go in details in numerical method and things like that. But another way, like what I showed you, is like you can decrease the step size. Yeah. We looked at boundary conditions. So there are like 3 types of boundary conditions: specified value conditions. So that's specified dependent variables, such as you specify the head, you specify the temperature, and this is called the Dirichlet boundary condition, or is known as type 1 boundary condition. So basically, groundwater flow is specified. Like, so I specify the head. So I tell him like the head at this x, y, and z and time is equal to this value. Yeah. And it could change in time. The specified head does not mean that's fixed in time or space. See, it's changing in space, x, y, and z, and it's changing in time. Yeah. Same with solute transport. Like I specify the condition, like so it's, at this x, y, z, and time, that is concentration. Then I have another type of boundary condition, which is not the specified value, but specified flux condition. So specified rate of flow, heat, mass transfer, and that's called the Neumann boundary condition. Dirichlet and Neumann, these are two German mathematicians. Yeah, I think, or I don't remember. No, this was a French mathematician, Dirichlet. I don't remember. Okay, just don't. I don't remember, but I know like at least one of them was a German mathematician. But anyway, that's where this name came from. Yeah. So groundwater flow, I specified the flow. So I specify the flux. Yeah. So the flux. So I specify the flux. So that's the unit of the flux. So K here, for example, like has remember like the flux here. Remember like the unit of this guy's length, the unit of this guy's length, and the unit of this guy's length over time. So specify the flux as like length over time. So you specify the flux. And here, for example, like you specify the mass flux. So that's like that would be like uh, the mass flux. That should be like, that's a subscript, by the way. So subscript. Okay. You specify the mass flux. So here, instead of like specifying like the head value, you specify the flux, and the head would be calculated accordingly. Like giving this flux, like this, giving this mass flux of contaminant, like giving this amount of contaminant that's entering through my boundary, then you can calculate, okay, so what would be the concentration? Versus here, you're saying, okay, like I want to maintain this concentration at this boundary, then the flux would be calculated. Then the model will calculate like the flux that will maintain this concentration. Here, your model will calculate, giving this flux, it will calculate the concentration at this boundary. And then mix it, or the dependent condition, flux dependent or on dependent value of the boundary, that's Cauchy condition or type 3. So groundwater flow head dependent. So basically, like I will say, I have a head in my river and I have a head in my on my aquifer, and is flux, the amount of water that will flow from the river to the aquifer or from the aquifer to the river will depend on the difference between like these two heads. So I specify like the like you specify the head, and then the model will calculate like this flux accordingly. So for the solute transport, like it is same, yeah. Solute transport concentration depend. So we like, you can look in detail in this lesson, but we had, for example, like exercise boundary condition. A specified flux boundary condition, Neumann boundary condition, defines which of the following boundary. So that's like the Neumann boundary condition. The value of the variable, e.g. head, the rate, so this is not the value of the variable, yeah? The rate of a change of the variable, yeah, the flux, yeah. How much flux is entering or leaving the system. The relationship between the variable and its derivative, both value and rate of a change of the variable and its derivative. No, so it is like the correct answer here will be B. Specifies the flux. I mean, specified flux should be obvious, yeah. So this should be easy question in the exam. In the context of groundwater flow, which is the following scenario would most probably be modeled using a specified flux boundary condition? A lake that maintain a constant water level. No, a lake that maintain a constant water level, that would be not how you do this. That would be like a specified head. An impermeable rock formulations that prevent water flow. Yes, because in that case the flux would be equal to 0. So in that case, uh, in in in, uh, in that case the flux would be like Qx would be equal to 0. Yeah, an impermeable block. So that in that case, like Qx would be equal to 0. Stream where flow rate is directly proportional to the difference in head between the stream and aquifer. Sorry, this is wrong. This is correct. Stream where flow rate is directly proportional, that's type 3. Well, where the head is maintained at specific level. Head is maintained at specific level, again, that's type 1, like specified. So that is type 2. Yeah. So this is like type 2. So that would be like type 2 boundary condition. Yeah. Again, one more. Yeah. Pumping well is injecting water into an aquifer. So now here I have Qx is equal to something. Yeah. How would you represent this groundwater model using Neumann boundary condition? So it is injecting. So that would be a positive flux value at the well location. Yeah. A negative is not negative because it's injecting is not withdrawing. A zero flux is not zero because I'm injecting something. A specified head value is in the word. So it is a positive flux. Yeah. I am injecting something. So that's a positive flux. And the heat transport problem is specifying the temperature at the surface. So now the temperature is specified as the surface. That's type 1. Is the example of which type of boundary condition? Specified uh, head. It is type 1, but it's not a specified head. I'm just specifying the temperature. Specified flux, type 2. Dependent mixed, type 3 is actually none of the above because it's not like a specified head, it is a specified temperature. So this part is correct, type 1 Dirichlet, but it's not like specified head, it's like specified temperature. I'm specifying like the temperature, so that would be like a type 1, none of the above. Yeah. So be careful, like that could be tricky. Yeah. Now, last thing we looked at. Yeah. So this is partially true because this is type 1, but we are not specifying that, we are specifying the temperature. Yeah. Now we looked at one thing is model calibration. So model calibration, you have like some data that you are observing in the field. You will develop your model and your model will simulate something. The objective of model calibration, of inverse modeling, is I want what I'm observing in the field to match what my model is outputting. And how to do this? You just play with the model, like you keep improving the model, either the mathematical structure of the model, the geological structure of the model, the boundary condition of the model, the parameters of the model. You keep playing with this, you keep improving this until like your model is capable of simulating what you are observing in the field. Once your model is capable of simulating what you are observing in the field, then you have a calibrated model. Yeah. So once your model is doing this, then you have like a calibrated model, and this calibrated model you can basically use like this model now represent your field condition, and then you can use it for engineering and management purposes. So that's like what you need to understand from here. Yeah. And how to goodness of it, like so we have like residuals. The residuals, that's the difference between what we are modeling and what we are observing. So here, this is what we are observing in the field, this is what we are modeling. So you see here, the residual here is this. The residual here is very small. The residual here, see, is very big. Like, see, the residual here is very big. The residual here is something. The residual here is a small. The residual here is a small. So basically, like, how could I calculate this? So the residual is the observed minus the simulated. So here you get like the observed minus the simulated. You square them. Why do we square them? Because like if that is negative and that's positive, they will cancel out. So that's why we square them. And then we take the square root. So that's called root mean square error. Yeah. So root mean squared error. So the error, that's like my residual squared because I squared it, and then I take the square root, and then I take the mean. Yeah, root mean square. And then you have like the sum of the squared residual. I just, instead of taking like a mean value, I just sum all the residuals. That could be also another matrix that you can use to evaluate how good your model is fitting, is like reproducing the observation there. And then you can have sum of squared weighted residual also. Weighted residual is basically like if some observation point are more important than the other. So only, for example, like maybe like these are all points that were not very accurate, or I don't care much about them, and I only and these are new points that I care more about. So I want to give this like more weight than this one. So here you can have like this weighting term for each point. Yeah. So that's also will give you control more on what you're doing. So the exercise calibration history matching is a physics-based model referred to running the model once with initial parameter. No. The process of adjusting the model parameter to match the observed. Yes. So you can adjust the model parameter, you can adjust the model structure, you can adjust the boundary condition. You just keep improving your model until your model is capable of simulating what you're observing in the field. Using a model to make prediction without comparison to data? Exactly not. Simplifying the model to reduce computation requirement. Also, that's not the main purpose for doing this. Yeah. What are the primary goal of calibration in a physics-based modeling? To make the model as simple as possible. This is not the primary goal. It could be a goal, but this is not like the primary goal. But it could be a very good goal. Yeah. That's one of the goal, but not the primary goal. So basically, like read the question. The question is saying what's the primary goal? Yeah, to ensure that the model accurately represents the real-world system. Yes, that's the primary goal. To reduce the number of model parameter. That could be also another goal for calibration. So this is the true answer, but this is not the primary goal. But that's also true. So this is the primary goal. This is correct. This is correct, but this is the primary goal to minimize the computational time required to run the model. Yeah, maybe also that could be maybe, yeah, maybe that could be also part of the calibration process, but not necessarily. But this is a calibration uh, goal for calibration. This is a goal for calibration, but this is the primary goal for calibration. Yeah. Okay. Okay. So that's all for this module.